Hey everybody, today we're going to be learning about delta epsilon proofs and function limits. Let's get into it. Now, before we get into proving limits using delta epsilon, it's important to understand what exactly a function limit is. Basically, a function limit denoted the limit as x approaches a of f of x equals L describes the behavior of the function f of x as x gets really close to a. Now, basically what that means, if we were to look at a diagram of this, is as x becomes closer and closer to a, we can imagine a variable delta such that if we take the interval around a that is denoted by delta, which I'm going to draw in here, we can have that a minus delta, and this would be a plus delta, and we have the area in between here would be from a minus delta to a plus delta. So basically, x is going closer and closer, and so if delta is closer and closer to 0, then x is going to be within these two bounds. So as x goes closer and closer, and delta becomes smaller and smaller, we can have that the value, not the value of the function, but how the function behaves will come to some tendency L. And it's important to note that the function doesn't actually have to exist there. It just has to behave like that as we lower the values of delta. And so it'll end up behaving like L, and that is why we say that the limit of f of x is equal to the L, describing the behavior, and not the actual value of f of x. And when we do our proofs, we're going to look more forward into this definition with delta, and we're going to introduce epsilon. Now that we know a little bit about our definition of a limit and how x needs to be close to a, we can have that x is close to a, remember from our definition of the limit. This is from the limit as x approaches a of f of x. And remember from previously that this means that x is between a minus delta and a plus delta, except possibly not at a. Because remember, we can take out the value of a, and the limit can still exist because it just describes the behavior and not the actual value of the function. So what we do end up having is that x is between a minus delta union with, a minus delta to 0 union with 0 to a plus delta. Or basically, the absolute value of x minus a is less than delta. That's just saying that the difference between x and a is no more than delta. And so we have that x is somewhere in this range between these two lines. Now the whole idea of the proof is that we can introduce the same thing, but except on what the limit equals. Because remember, we have that this is equal to L. We need to prove that it's equal to L. So what we can do is take the same thing with L. If we were to imagine an interval around L, and instead of using delta for this one, we're going to use epsilon. So now we have an interval on L. And the idea of the proof is, if we can take a generic epsilon, so it doesn't matter what epsilon is, which means epsilon can be arbitrarily small. If we're taking any epsilon, it has to work for every single epsilon. Basically, what that means is we can make epsilon as teeny tiny as we want, and this should still work. So the opening of our proof would be for all epsilon. We're going to use the symbol upside down A. That means for all. So for all epsilon. And epsilon has to be greater than 0, because if epsilon was 0, there is no limit there. There is no space in between. That would just be saying that it's equal to L. And we can't have that because we're trying to prove that it's equal to L. And we can't assume our proofs. So basically, the whole idea of the proof is we're going to move these bars down. We're going to take these bars, move them as close to L as we can. And if we make them really teeny tiny, and there exists some delta such that if x is within here, then the difference between f of x and delta, sorry, the difference between f of x and L is less than epsilon. So we need the absolute value of f of x minus L to be less than epsilon. And if we can prove that this is true for all epsilons, given that we have x's between here and here, then we have proven that the limit is true. As we can imagine these constraints coming in closer and closer and closer. And basically, it just kind of squeezes the whole thing. Sorry. And it just kind of squeezes towards. And so what we end up with is that the limit is indeed equal to L. So the idea of the proof in formal words is that for all epsilon greater than 0, there exists, it's the backwards E, there exists a delta such that when x is really close to A, or absolute value of x minus A is less than delta, that means that L is really close to f of x. That means that f of x minus L is less than epsilon. And this right here is the formal definition of the proof. We have all sides closing in on that limit, and we're going to take an arbitrary epsilon, and we can choose what our delta is, and we just have to prove that we can put all the x's in that interval such that f of x and L are so close together that the difference between them is less than an arbitrarily small constant, which we call epsilon. And we're going to get into that process next. Now that we know about the proof, let's apply it to prove that the limit as x approaches 2 of f of x equals x plus 2 is 4. And so let's take a look at this graph. From our proof, we needed to prove that there existed a delta, or there existed an interval here such that if x was within this interval, then for all epsilon, then f of x minus L was less than epsilon. So let's write down the formal definition of our proof. We needed to prove that for all epsilon greater than 0, there exists a delta such that if the absolute value of x minus A was less than delta, then the absolute value of f of x minus L was less than epsilon. So in this case, what we have here is that our L is equal to 4, because we're trying to prove that the limit's 4. And we have here that our A is equal to 2. So our goal is the following. Prove that for all epsilon greater than 0, there exists a delta such that when the absolute value of x minus 2 was less than this delta, that implies that f of x minus 4 was less than epsilon. And in this case, our f of x was, what was our f of x? It was x plus 2. In this case, x plus 2 minus 4 less than epsilon. So as with most proofs, we're going to start by assuming our givens. So we're given epsilon greater than 0. And we need to prove that there exists a delta, so we're going to let delta equal something. But for now, we're going to leave it blank. We don't quite know what we want to let delta equal yet until we do some of our work. Now, if we assume that x is close to 2, or x is close to a, or in this case, the absolute value of x minus 2 is less than delta, then we can consider our condition. We need the absolute value of x plus 2 minus 4. Let's do some rearranging of this. This is clearly equal to x, absolute value of x minus 2. Oh, but would you look at that? In our assumptions, we have assumed that the absolute value of x minus 2 was less than delta. And what we see here is that the absolute value of f of x minus 4, which is x plus 2 minus 4, is equal to that. We know for a fact that that is less than delta. And this is equal to absolute value of f of x minus L. And our goal was to prove that the absolute value of f of x minus L was less than epsilon. So there you can pick whatever you want for what your delta is. So in this case, all we can do is we can simply pick that our delta is equal to epsilon. And we have that f of x minus L is less than epsilon. Because f of x minus L is equal to x plus 2 minus 4, which is equal to the absolute value of x minus 2, which we know, because we assumed, is less than delta. And we can pick delta to be anything, and so we just picked it to be epsilon, and thus we have proven for all epsilon, there exists a delta such that x being close to 2 implies that f of x minus 4 is less than epsilon. Therefore, it is proven that the limit as x approaches 2 of x plus 2 is equal to 4. Would you look at that? This one was a really easy example because we just so happened when we were doing some of our rearranging that we ended up with the exact thing that we assumed. It's not always going to be like that, and we'll get into some examples after, but look at how nice that was. Let's get into some harder examples now. All right, so here's our second example. We need to prove that the limit as x approaches 0 of x squared is equal to 0. So in this case, we can clearly see that our L is equal to 0, and also that our A is equal to 0. So now we can write down our goal. Prove that for all epsilon greater than 0, there exists a delta such that if the absolute value of, well, x minus a, but a is just 0, so x minus 0 is less than delta. So if x is close to 0, then that must imply that f of x minus L, which is also 0, is less than epsilon. So that's our goal. We need to prove that. So let's go and assume our givens. Given epsilon greater than 0, keeping it arbitrary, let delta equal something. We'll pick what it is once we do a little bit of work. And we will assume that the absolute value of x minus 0 is less than delta, or x is close to 0. This basically is that just the absolute value of x is less than delta. Then, let's consider our absolute value of f of x minus L. That's equal to f of x in this case was x squared. Absolute value of x squared minus 0. And that's just equal to the absolute value of x squared. Now, here you got something different. In our previous case, we ended up getting back exactly what we assumed. But in this case, it's just a little different. In this case, we can use some properties of the absolute value to get what we want. We want to get somewhere in here, we want to get absolute value of x, because then we can compare it with delta. And I know that by properties of the absolute value of x squared is just the same as the absolute value of x all squared. And now, since I know that the absolute value of x is less than delta, I can say that the absolute value of x all squared is less than delta squared. And so now, by doing this chain, we have that our f of x minus L is less than delta squared. And since we can pick whatever we want for delta, we can just pick something that will turn delta squared into epsilon. And so we can just pick delta to be the square root of epsilon. And if we pick delta to be the square root of epsilon, what we end up getting is the square root of epsilon squared equals epsilon. Alternatively, if you couldn't see that, once you get to this point, you know that you want delta squared to be equal to epsilon. This is in your side work. You know that this wants to be true, so now you can just isolate if you couldn't see that from the start. But now we have that the absolute value of f of x minus L is less than epsilon, and so we've proven the limit. So we're done. Thus we have that x minus a less than delta implies the absolute value of f of x minus L less than epsilon. So it's proven. And you're done. We'll do another harder example after this as well. But now we're just getting into some of the tactics you can use to prove these. It's the same thing every time. You're going to get harder and harder functions. But the main idea is you want to somewhere manipulate your absolute value of f of x minus L so that you can grab whatever you're comparing to delta, so you can put delta in there somewhere. And that is the main goal. I'll show you another example of this, which takes a little bit more thinking than just taking the square root. Next. Right, now let's take a look at our harder example. Now you know the drill for the beginning. We got to figure out what our L and what our A is. In this case, our L is 6 and A is equal to 3. Now let's write down our goal. Same as usual. We need to prove that for all epsilon greater than 0, there exists a delta such that if the absolute value of x minus 3 in this case, because our A is 3, is less than delta, that implies that the absolute value of f of x minus 6 is less than epsilon. That's our goal. Now, same as always, let's state our assumptions. We're given epsilon greater than 0. Let delta equal something. We'll get back to that. And we can assume the absolute value of x minus 3 is less than delta. It's a bad 3, sorry. Or x is close to 3. Then, let's take a look at our condition. We need the absolute value of f of x minus L that is equal to f of x is x squared minus 2x plus 3 minus 6, because L is 6. Now let's do some simplification. This is equal to x squared minus 2x minus 3. And this doesn't look great. Our goal here is we want to try to get this into this. We want to get our x minus 3, because then we can compare it to delta and choose delta to be something that gives us epsilon on that side, so that we can prove that absolute value of f of x minus L is less than epsilon. But in this case, we don't have that sort of thing, and we don't find the absolute value of x minus 3 appearing in our answer. And when it comes to the quadratic stuff like this, usually when factored, it'll actually give you what you're looking for. So I'm going to go ahead and factor this. X squared minus 2x minus 3 factors out into x minus 3 and x plus 1, I believe. Yep. And then using our properties of absolute value, we can say that this is equal to the absolute value of x minus 3 times the absolute value of x plus 1. And there we go. There we have it. We have our absolute value of x minus 3 in there. We've figured it out. But what do we have here? We've got an extra absolute value of x plus 1 that we can't really do anything with because we haven't got anything to compare it with. So let's do some side work. Let's pull in the side. What do we do with this absolute value of x plus 1? What do we do with it? Now here's the trick. What if we could compare the absolute value of x minus 3 to some number so that we can put a bound on x and then end up finding absolute value of x minus 1 as a result? Well, good news, because we can. The trick is to take delta to be the minimum of two numbers. One easy number, like 1, and then one number that will most definitely have epsilon in it so that you can finish your inequality. But by taking delta to be the minimum of 1 and some other thing, we have guaranteed that delta is less than or equal to 1. Do we see how that works? Because either delta is equal to 1 or is less than 1 by the minimum function. And so, since we know the absolute value of x minus 3 is less than delta, and delta is less than or equal to 1, we have the absolute value of x minus 3 is less than 1. Now, we can work with this to find something for the absolute value of x plus 1. Since the absolute value of x minus 3 is less than 1, this gives us information. This tells us that x minus 3 is between -1 and 1, and so if we add 4 to the entire inequality, just to get x plus 1 in there, we end up getting 3 being less than x plus 1 being less than 5. We end up with x plus 1 is less than 5. And that implies that the absolute value of x plus 1 is less than 5. And would you look at that? Now we have a bound for x plus 1. Take a look. You can see that by picking delta to be the minimum of 1 and some other number, we were able to find a bound for something entirely unrelated to our assumption via x. And now that we know that having delta be the minimum of 1 and some other thing implies that absolute value of x plus 1 is less than 5, we can plug that into our inequality and continue our chain. Because now we know that this is less than x minus 3 times 5. Because we just showed that the absolute value of x plus 1 is less than 5. And look at how far we've come now. And now we're left with our absolute value of x minus 3, which we have directly compared to delta, and just multiplied by a constant. Take a look at that. One of the mistakes that people do here is they will just plug in delta as absolute value of x minus 3 right here, and then just say, oh, I know what to do. I'm going to set delta equal to epsilon over the absolute value of x plus 1. Oh, because then if I multiply this by the absolute value of x plus 1, these guys are just going to cancel out, and I'm going to end up with delta just how I wanted. No, don't do that. You can't do that because we still have variables in here. We still have x as a variable. And since our delta is supposed to be constant, we can't declare it in terms of a variable. And that's a very common error. So you actually do have to take it as a minimum of preferably 1 as the easier number to work with, to find a bound on the other thing so that you can replace it with a constant. Because remember, we want our delta to be constant and we can't declare it in terms of a variable. But now that we're here, let's replace our absolute value of x minus 3 with a delta, because we know it's less than delta, times 5. And would you look at that, we're almost there. We just need to find a value for delta that'll give us this. And I believe that value we're looking for is epsilon over 5. Taking the delta value to be the minimum of 1 and epsilon over 5, we can replace that with, this will be less than or equal to, because remember, if delta is the minimum of 1 and epsilon over 5, that means it is either equal to epsilon over 5 or it is less if 1 ends up being less than epsilon over 5. So now we can replace our delta with epsilon over 5 times 5. When you look at that, you end up with exactly what you need. And through this pretty long chain, we've ended up with the absolute value of f of x minus L is less than epsilon. And that is our whole proof. Now you can just write your final statement. Thus, absolute value of x minus 3 less than delta implies absolute value of f of x minus 6 is less than epsilon. And so you've proven the limit and you're done. Just to summarize, if you ever get caught up with extra variables, don't try to set your delta to be equal to something with a variable in it, because delta is supposed to be a constant. You're going to want to set delta to the minimum of preferably 1. I'll choose 1 every time because it's just an easy number to work with. And whatever you're going to pick in the end. So that way you can end up with a bound on any variable that you're left with, and you can end up with a nice clean proof that proves that the absolute value of f of x minus L is less than epsilon. That's all I have today. Thank you so much.